Well, welcome everybody to the 21st talk in our seminar series. And today I'm happy to introduce Blake Barker. He did his PhD in 2014 with Kevin Zumbrun at Indiana University, and then got an NSF Postdoctoral Fellowship, and went to Brown to work with Bjorn Sandstede. And I think 4 years ago, he took a position at Brigham Young University, where he still is. And he's really an expert in computer-assisted analysis of stability of traveling waves in PDEs, in particular using the Evans function approach. And I think all these things we'll hear about in today's talk. Well, Blake, I'm looking forward to your talk. Go ahead.
All right, thank you, Jean-Valley. So today I'm talking about our ongoing work improving stability of traveling waves in the 1D Navier-Stokes equations. This is a project that began some time ago, and we've made some recent progress that puts the end goal in sight. Now we're very close. This is work with Taylor Paskett, and he was an undergraduate working with me here at BYU. Now he's a master's student here, and with, of course, my PhD advisor, Kevin Zumbrun. And we'd like to thank the NSF for partial support, as this was work that started when I was still a postdoc. So what is the motivation? So you look in nature and you see traveling waves all over the place, right? And some of them may look chaotic. Some of them have patterns that are very distinct. And you see these patterns and you think about the PDEs we use to model them. And the natural question is, are the solutions that appear to correspond to these phenomena in nature stable? If these solutions are stable, then you would expect to see the analog in nature. And if they're not stable, then you would think that you would not have this correspondence between the waves that you actually observe in nature. One of the motivations for this, of course, is just to understand just to understand physics, just to understand the PDE equations, but also in hopes that it can provide information that can be useful in engineering applications. For example, I like this example here on the right, Operation Sailor Hat. After World War II, the US had a bunch of extra naval ships, and they wanted to see what was the effect of an atomic bomb on these ships. So they used just regular TNT, but 500 tons of it on this island in Hawaii, in the Hawaiian Islands, and they blew it up. And you can see the shock wave going out across the water, and then you can see from the cloud too. Anyways, it left a great big crater. So I guess the hope would be that if we can provide verification of a model, then that model could be studied in place of some of these expensive experiments, blowing up $1 billion ships, for example. So the equations we're looking at today are the 1D compressible Navier-Stokes equations. We're looking at them in Lagrangian coordinates. T is corresponding to time and X to spatial location. V corresponds to specific volume, U to velocity. E is the energy. It's given by the internal energy, little e, plus velocity squared over 2. And then we're considering an ideal polytropic gas equation of state. And so the pressure function takes a very simple form. It's the Grunessian constant times the energy divided by the specific volume. And then it turns out energy and temperature related in a linear fashion, just by a constant scalar. Notice this is a hyperbolic parabolic PDE. And what we're interested in is proving stability of the traveling wave solutions to this. What we'll do is a coordinate change where we'll take x to x minus st, where s is the speed of the traveling wave we're looking for, the background traveling wave. And then our traveling wave will be a stationary solution of the resulting PDE equation. So that's what we do here. We make the ansatz that the solution takes this form, where s is the speed of the wave. That gives us the PDE in the traveling wave coordinates. So now the traveling wave is a stationary solution. So we set these time derivatives equal to 0. And that gives us an ODE, the profile ODE that we can solve. And then here we've got on the left in this figure, the profile ODE. Now, if you look at the top equation, when VT is 0, oh, that's a typo. That far right should be minus u sub x. So when you set VT equal to 0, you see that there's this relationship between u and v. And so for the ODE that we solve for the profile, it's actually just a two-dimensional ODE. So we solve for it in the coordinates v and e. And this is for, we do a rescaling so that we can take without loss of generality v at negative infinity equals 1. And then here on the right, we have the phase diagram. So at negative infinity, the lower right dot gives us the fixed point, and that corresponds to a source. And then at the top left, you've got a saddle that corresponds to the profile at positive infinity. When we solve for the profile, we'll be using a standard contraction mapping principle with Duhamel's principle in order to obtain an enclosure of the profile solution a little bit away from the fixed point along that connecting orbit between the fixed points. And then we'll solve in backward time, because in backward time, we'll be solving towards a stable fixed point. Something nice about the profile by Gilbarg's argument is that it lies between these two null lines that are drawn in red. And then in the middle there, we've got the dotted line that gives us the profile. And so in particular, from examining these null lines, you see that the solution is monotone. And anyways, it's nice. It's a nice profile to try and solve rigorously. Okay, so we mentioned that we're interested, now we've got the profile, not yet rigorously, but we've got the profile. We're interested in the stability of it. So what do we mean exactly when we talk about the stability of these traveling waves? What we mean is that if you perturb them a little bit, that as time goes to infinity, they'll converge back to a translate of the original traveling wave. Now here we've used a mean zero perturbation, so it actually converges back exactly to the original traveling wave. But this provides the idea. So we're talking about nonlinear stability of these traveling waves. These pictures are courtesy of two undergraduate students that I mentored, and are indeed for the system we're looking at. However, this is in Eulerian coordinates, but it gives the idea of what we mean by nonlinear stability. To be precise, we say that a wave is spectrally stable. Okay, right. So the condition, it turns out, that we need to look at is what's called spectral stability. And we'll see here in a moment that spectral stability implies nonlinear orbital stability, but to be precise, we give the definitions. So a wave is spectrally stable if the eigenvalues of the PDE eigenvalue problem that you get from linearizing the PDE about the background traveling wave, with the exception of the zero eigenvalue that you always have corresponding to translational invariance, have negative real part, then it's spectrally stable. And a wave is said to be asymptotically orbitally stable if sufficiently small perturbations of the wave converge to a spatial translate. That's what we described with this picture. So it turns out that spectral stability will give us this nonlinear orbital stability property that we've demonstrated with the figure. We note that, so we have a mixed audience, so I'm giving background to try and reach everyone. Some of you, this is quite familiar with, but what we mean by, or the comment about translational invariance is this. It turns out that the derivative of your profile is actually an eigenvalue of the PD eigenvalue problem, and it corresponds to the eigenvalue 0. So you always have that 0 there. Okay, so here's the theorem that I mentioned. Spectral stability implies asymptotic orbital stability for a wide variety of PDEs, and in particular for the one we're looking at. So if D is your PDE operator, and you're looking for a stationary solution of it, given by the traveling wave, then you linearize about that traveling wave, and it gives rise to a PDE eigenvalue problem, so a linear PDE problem. And if there are no eigenvalues except for the one with 0 that have that don't have negative part, then it's spectrally stable. So if all the eigenvalues have negative real part except for the 0, 1, it's spectrally stable. There are a number of references here that provide background on this theorem. So my PhD advisor and several of his collaborators have worked with conservation laws and shown this nonlinear stability theorem. And of course, there are other systems besides conservation laws and lots of other people we could reference, but specific to the problem we're looking at, these are the relevant references specific to our problem. And then one other study that we need to carefully mention is this one by Humphreys, Ling, and Zumbrun in 2009. So they're looking at the model we're looking at, but they're not using rigorous computation, they're using double arithmetic for the computations that show spectral stability. They also have a small amplitude spectral stability result, as do Freistuhler and Smolin. So what we're looking at is rigorously proving spectral stability to imply nonlinear orbital stability for large amplitude waves in the 1D Navier-Stokes equations. So the eigenvalue problem for the PDE is given by the following. Bar represents the background traveling wave solution that we've linearized about. And as you can see, this is a linear PDE. Actually, it's an ODE now, because when we change it to an eigenvalue problem, we lose the time derivative. Since it's 1D, we actually just derive it at linear ODE, which we can write as a first order system. So we'll change this ODE to a first order system and solve for it that way. So the eigenvalue problem can be thought of as looking for solutions of this linear ODE that satisfy a decay rate as x goes to plus and minus infinity. And because the traveling wave converges asymptotically to a constant state, the matrix A as x goes to plus and minus infinity also converges asymptotically to a constant state. So here are the challenges in computing for solutions to this ODE. It's a boundary value problem on an infinite domain. So for one thing, you have to be careful about the getting your solution a little bit away from infinity. Of course, this is something that this group is very familiar with. It's, in fact, I debated if I should put it under challenges talking to this group, because it's a group that does this all the time, right? And then here's the actual main challenge, and that is that there are competing scales generally. So as a very simple example, if you have just a diagonal system, then the solution takes this form here for W. And you can see that if you are solving for a solution initialized with some component of B1 and some component of B2, that as you solve that forward in time from negative infinity, that you're going to lose the part of the solution in the direction of B1 due to the differing scales. You're going to lose it at machine precision eventually. And that's the main challenge with these type of computations, even with double arithmetic. So we do the standard thing and get the solution away from infinity with some sort of analysis around the fixed point. And then we'll solve the ODE system in a way that can handle the competing growth modes. Okay, so if one option would be to just try to solve the Evans function as a boundary value problem and find eigenvalues and eigenvector pairs. But we want to be able to rigorously say, with as a proof, that the wave is stable. So we need to prove there are no eigenvalues in the right half complex plane for the eigenvalue PDE problem. And so that gives rise to the Evans function. The idea of the Evans function is the following. Instead of solving for an eigenvector-eigenvalue pair, we'll solve for a basis of the ODE solution space that is tangent to the unstable manifold at negative infinity, and then we'll solve for another basis that is tangent to the stable subspace at positive infinity. So we'll solve that one in backward time. So we'll solve in forward and backward time from negative infinity and positive infinity to x equals 0, say. And then we'll take a determinant. And if that determinant's 0, it corresponds to there being a linear combination of those bases connecting the left and right end states. So it corresponds to an eigenvector. And the lambda value for which that happens, for which d of lambda is 0, corresponds to the eigenvalue. However, if we're careful to initialize the basis of the Evans function with in an analytic way, depending on lambda, then that basis varies analytically, and so the Evans function varies analytically in lambda. So it's analytic, and we can use winding number computations. So then instead of trying to find d of lambda equals 0, we use some method to bound the modulus of admissible unstable eigenvalues. We compute the Evans function on a contour that encloses that bounded region. And if that winding computation is 0, if the winding number is 0, then there were no eigenvalues and the wave is spectrally stable, hence nonlinearly orbitally stable. The nice thing about getting a bound on that region of admissible unstable eigenvalues is that it was done in that paper by Humphreys, Ling, and Zumbrun. And it's a condition that you can just compute with interval arithmetic and it gives you your bound. So that part's already done for the system. Okay, so how are we going to deal with the competing growth modes we talked about? So we'll use the compound matrix method. So let's say that you want to solve for a k-dimensional subspace of an n-dimensional space like we described. Then you can use the exterior products to lift the linear ODE system to an n choose k-sized ODE system. Our system is 5 by 2 and 5 by 3. So in the end, we get a 10-dimensional ODE system for the linear Evans ODE system. And then you just follow a single vector this time. Instead of a subspace of dimension 3, say, you're following a single vector that corresponds to the largest real part eigenvalue. And then you can scale that out so that your solution has no growth, essentially. Near infinity, it's just constant, more or less. And you can solve it that way. And that's what we do for this system. One of the things we have as a goal, we have our sights on, is being able to rigorously compute with continuous orthogonalization. So continuous orthogonalization is a method that Humphreys and Zumbrun came up with, where you use continuous orthogonalization as has been done in the past by others, but you do it in a way that tracks, it allows you to track the analyticity. So in the end, you have the scalar ODE that goes with it, and you use that to regain analyticity of your orthogonal basis that you get at x equals 0. So you're able to still maintain an analytic Evans function. And the nice thing about this is that it doesn't grow as n choose k. So for very large systems, say systems that are 20 by 10, 20 dimensional with a 10 dimensional subspace, you can still use this method. Okay, great. So we've set up, okay, we've given all the background now for the Evans function. So now how are we going to rigorously enclose the solution of the Evans function? I'm going to start with the linear ODE for the Evans function first, and then in a little bit we'll explain how we rigorously enclose the profile. But let's start with the ODE for the Evans system. What we're going to do is use a method that's inspired by Townsend. So the idea is we're going to approximate the matrix A. By the way, we're just fixing lambda. Lambda is a parameter here. We're just fixing it. Okay, so now we're just having an ODE depend on x. And we're going to approximate 8 hat of x, say with a polynomial for each entry. And then we're going to solve for z prime. So we're going to solve almost the right system, but we're going to solve it with the initial conditions being the identity matrix. So we're solving for a fundamental solution of this approximating ODE. And we're going to compare the error as if we were solving for a fundamental solution for the ODE we care about. If you take the derivative of this last equation, then you get the ODE prime satisfies, and you rearrange it, and you see that this is going to satisfy the error bound we have here at the bottom of our screen, just using standard ODE error estimates. For example, see the paper by Brouwer. So this method we've tested, and Taylor, the undergraduate, now master student that's been working with me, has tested, and it works really well. You just have to take small enough steps in X that this error doesn't grow too big. How do we solve for this Z? So it's straightforward, I should mention. It's straightforward to find the error between A hat and A tilde. So how do we get a rigorous enclosure of Z? We just use a series representation of Z, and it's not too terribly hard to bound the error, the tail end of that series. So you see that this is going to be your equation for the coefficients, and then to bound the error, we just have the following assumption, that there is a condition on the first n terms of your series. And then you get this bound on the tail end using a geometric series. So it's a straightforward condition to check. Okay, so that's the way we compute the Evans function. And now to talk about how we compute the profile. So I've seen enough of these talks to know that the way one would approach this problem is to use, say, the parameterization method to bring your solution out away from infinity. And then one would use the radii polynomial approach in order to solve on an infinite dimensional space for the profile. I do it a little differently, and the main reason why is because I started looking at this clear back before I was aware of when I was just starting off with this stuff and was aware of these other methods, but also because it turns out to be pretty straightforward just to get a series solution with a bound on the tail. And so that's the way I do it. The other thing to keep in mind is this, as I mentioned earlier, when we were looking at the phase diagram for this profile is pretty nice in that when you solve from v plus and backward time, the solutions are sort of bunching up close together. And so that's a nice property that helps with solving this. So here's our ODE for the profile with the n states at plus and minus infinity, denoted by a minus or plus subscript. And then we look for a series solution, which gives us the following recurrence relation for the coefficients, where the star represents convolution. What we'd like to do is bound the tail end of this. Now, one way we could try to do this is to look at the first, say, n terms and show that each successive coefficient in norm is less than some constant to the n power, right? So we could get ourselves set up for a series solution and use the just use a geometric series to bound the tail end. The problem is this convolution involving three terms here on the left for En. So we've got v convolved with itself twice. And if we just try to set up the geometric series by saying the coefficients are less than okay, yeah, so there's a question, what is gamma here? It's the Grunetian constant. So it's a parameter corresponding to the gas, the type of gas that you're looking at. And it's going to be between probably like 1 and 3, or 2/3 and 3, and 2/5 is another example. Okay, so if you're trying to use just a geometric series, then you're going to end up with n squared times your c to the n term you're looking for from that convolution. So that 1 over n that you get to multiply on the outside of the parentheses isn't enough. But it turns out if you try to bound each coefficient by some constant to the n divided by n plus 1, then everything works out. And so that's what we do. So first off, we just need a few lemata to help us prove this, some pretty straightforward things. So for the convolution, we need to be able to bound that convolution. So under the assumption that the terms are of the series coefficients, under the assumption that their norm is bounded by a constant to the n over n plus 1, then we're going to have something like this that we need to use. And it's just going to be straightforward to check using calculus that it's less than this term that involves log. And now this is nice because, of course, n will dominate log. So that took care of that issue we described if we didn't try to divide by n plus 1 in our bound. Okay, so another thing that we need is, okay, so using that lemma that we just looked at, we can now say something about the actual convolution of coefficients. And again, this is just standard manipulation of series, and then using our lemma to change it to a log. Then we've got to do the same thing with that convolution that involves three terms. We're going to end up with a log n squared term, but that's okay because it'll still be divided by n. And then here we're just pulling out some of the first and final entries of the summation so that it looks like our previous lemata. We apply those, and in the end we get a bound that depends on log and log squared, but divided by n, so that we take n large enough and that term will be as small as we want it to be. So we define H, V, and HE to be the terms that we want to be less than 1 from that previous slide. So these terms that we got here in the square brackets we'll define to be HV and HE, but they've been rearranged just to make sure we get the right form we want. And we're able to use those to show by induction that our coefficients are bounded by some constant m times our constant c to the, that should be c to the n over n plus 1. Sorry, another typo there in the statement of the lemma. Anyways, so what we do, our strategy is that we use interval arithmetic to compute the series coefficients far enough out that those log terms are dominated by n and less than 1, essentially, so that we can conclude that the coefficients are indeed bounded by a geometric series. But then when we actually compute the profile, we don't have to go that far out. We just go out far enough that the error is as small as we want. This method worked fairly well. So we get a enclosure. Oh, I do use a grid. At each step, I'll use a grid because the wrapping effect seems to grow on the order of, say, 10 squared with each step of size delta x equals 1. But when I break it up into a grid, so our initial condition is a grid of 10 by 10 or so, or 100 by 100, then the wrapping effect grows such that you lose very little with each step. Anyways, in the end, we've got the profile all the way from a finite value near plus infinity to a finite value near negative infinity with an error term of 10 to the negative 8, which I believe will be enough for the Evans function computations. One never knows till one does it, but I think it'll work. We could always try setting it up as a contraction mapping boundary value problem if it's a problem. But anyways, so this was exciting to get this done, because now we should be able to finish this off pretty quick. Okay, so there's one other thing we need to talk about, and that is, now that we have a way for getting a rigorous enclosure of the Evans of the ODEs, and we take a determinant, pretty straightforward, right, with interval arithmetic. So now we have this rigorous enclosure of the Evans function at points. How do we guarantee that the winding number is 0? So for that, what we do is parameterize the contour on which we want to compute the Evans function by pieces, where each piece is parameterized with a real variable that goes between -1 and 1. And we use Chebyshev interpolation. And this is a group where I don't need to give much detail on that. So we're going to use Chebyshev interpolation of the Evans function. We'll use the notation of Tadmor and Reddy and Weidemann. One could also look at Tadmor's analogous result to get a bound. So if we're interpolating between -1 and 1, we just have to bound modulus along an ellipse, as this group's familiar with. And that will give us a bound on our interpolation error for this analytic function. And of course, that interpolation error decays at exponential rate with respect to capital N, the number of nodes we use in the Chebyshev interpolation. We actually used this interpolation for isentropic gas, and it worked really well. So this part I expect to be straightforward. So what's left to do? Now that we've got the profile, we've got a way to compute the Evans function. There's already a way to get the bound on admissible the eigenvalues. We just need to put it together. So the profile, I finished this a couple of days ago, so we just haven't, I was hoping to get it all done for today, but you know how things go. So that's the future work. We'll be putting these last little pieces together. And then one of the things that we haven't done yet is solve for regions of parameter space. I know that there are methods people in this group use for that. So we could try those, for example, or we could try something similar to the Chebyshev interpolation we were using, but in multi-variables with parameters as variables. We would like to develop a rigorous integrator for continuous orthogonalization so that we can treat larger dimensional systems. This is already getting to sort of the extreme for using the compound matrix method. We want to be able to treat systems that are like 20 by 10, say for example, the reactive Navier-Stokes equations with multi-species or MHD. And that would be a more complicated systems. We'll be applying it to more physical systems that are even larger dimensional, have more terms, are more complicated. Fortunately, for some of those, the profile is the same, so there's a little bit of work that will carry over. And with that, I would like to thank you for being here with me.
Hey, Blake. Thank you.
Very nice.
Very nice. So there's plenty of time for questions because Blake was pretty quick.
I always talk faster when I'm giving the actual talk.
So if someone wants to ask a question, please.
Yes,
Go
I
ahead.
have a question.
Michael.
Thank you. So you talked about these contour integrals, but maybe you said, but I did not quite get which kind of contours are you taking? You actually want to prove that there is no eigenvalue in the right complex half plane, in the full complex half plane. So can you do that by contour integral?
That's right. So we're generally using a half circle. So we'll take a circle that is large enough in the right half, that's centered at 0. So we'll take just the part of a circle, a half circle that's in the right half plane and centered at 0 and has a radius that's sufficiently large to ensure that any admissible and stable eigenvalues are enclosed in that circle. Then we'll compute the Evans function on that contour and look at the winding number of that image. And that winding number gives us the number of eigenvalues, right? As you say.
So does that mean that outside of that circle, you have some pen and paper estimate that rolls out?
That's the point. Yeah, that's what I meant. Well, how do you decide if this radius is large enough?
Right. Okay, great. Right. So for this one, we don't, there's not much work here. We just have to implement with interval arithmetic a bound given in that paper by Humphreys, Ling, and Zumbrun. They use, they're not using energy estimates. They're using my mind just went blank. It's called a tracking estimate, right? So it's a tracking estimate. The idea is that you sort of bound with cones analytically the solutions emanating from plus and minus infinity, and then for sufficiently large lambda at x equals 0, those cones don't intersect, and you can say that there are no eigenvalues for lambda larger than that radius.
And you can quantify these
right.
Sufficient what you are saying.
Right. So yes. So the condition they have is a condition that comes down to evaluating a few terms, and it's explicit. And so yeah, it's really nice what they've done. But another way we often look at is with energy estimates, as I know you and others have done as well.
So that means that actually by some means, which you just briefly described, you can show that all the critical stuff happens within a compact subdomain of the right complex half plane, and on that compact subset you work with computer-assisted methods.
That's right. That is correct.
Then my world is in good order. Thank you.
Yes. Yeah, I kind of breezed over that one since Humphreys, Ling, and Zumbrun did all the work there. But that's a good point. Thank you.
Other questions? I have a question, Blake. So
Yes.
you're saying you just want to finish off the project.
Uh-huh.
So that can either be just a couple of days work, or it can be wildly optimistic, right? So so do you expect to that there might be some difficult pieces here, or?
Oh, well, experience has told me that you always run into difficult pieces as you do it. So my optimism is that Christmas break will be relaxing and we'll get it done then, but
Okay.
but we'll see. Yeah, but this was the major thing. Like the two major pieces are done. So I don't think anything else will be a major issue. It's just it'll take time, right? It's the standard things. You do something, you see that you've got to do a little more work to control the wrapping effect in the way you code it or something like that. I think it'll be okay going forward.
So I have a question.
Mm-hmm.
Yeah, so regarding the profile, you mentioned that, so this piece, the profile itself, so you have the rigorous proof of it.
Uh-huh.
Right. So what kind of error bound do you have in terms of numbers? Like,
oh, okay. So well, let's see, maybe I can show you. So it started off, hold on.
yeah, I mean, I guess a bit of details, like how many Taylor coefficients, what is the rigorous error bound that you have for the profile, just figure yourself.
Yeah, so we're starting at, let's see, can you all see that? So we're starting at x equals 26, and we're going to x equals negative 26, which gets you really close to the fixed points for these parameters.
Mm-hmm.
So we start off with, so from, basically you have an enclosure of the solution at 26 by the contraction mapping principle, using Duhamel's principle, that is on the order of machine epsilon.
Mm-hmm.
So after you, I guess it was actually 27 we started off. So with one step, this is your error bound. So you see that you are losing a little bit. It's going to lose less error when we get a little further away, because right now we're near the saddle. Eventually we get to what's the sync and backward time. And so then you start to see that you lose a lot less after a little while. As far as the number of computations, it takes about anywhere from 100 to 400 computations of the coefficients in order to say that that log n over n term is, log squared over n term is sufficiently bounded. But then for the actual computation to get machine epsilon error, it only takes about 20 to 25 coefficients generally is what I've seen. So that's nice.
Mm-hmm. And the profile boundary error, what is that?
The error on the profile boundary,
Mm-hmm.
that's going to be machine epsilon.
Okay.
Yeah. So you just go out close. You just keep going further out towards positive infinity until it's as small as you want, and with the contraction mapping. So we just do it at about machine epsilon.
Okay. And for instance, the whole computation of the profile with interval arithmetic, how long does that take?
Okay. So right now it's taking about, this one's taking about 20 to 30 minutes, which is quite a while for this. The thing that's slowing it down is the way it's actually taking probably 90% of the computation time. The way that I have, so I'm pushing the solution forward with a bunch of different subintervals, so that it controls that wrapping effect on that one step. And then I have to combine all of those. Let's see, so I guess it's 100 by 100, so 10,000, which I've got it set up so in IntLab, it computes really fast because it's vectorized. But then it has to combine all of those into the union of all of those subsets at the end of your forward step is what's taking a long time, because as I said, I did this 2 days ago and I haven't figured out the way you're supposed to do that yet in IntLab.
I see. Okay. Thank you.
Yeah.
Are there any other
I
people
would
with
have it.
questions?
I have another one. So again, maybe you said it, but I don't remember. Before proving stability of traveling waves, you analytically you need existence of these traveling waves. Is that easy in your case, or did you do that by other computer-assisted means, or did you not do it at all? Or?
Thank you for that question. I did forget to mention it. So it's actually been proven analytically by Gilbard that profiles exist, and it's because of, you can do it because of the null-clines. So let me go back to that picture. It just disappeared on me. But it happens with Zoom. Well, with Zoom, I can't see. There we go. So I can't actually see it as I scroll. Okay, so let's go back to the picture of the null-cline. So Gilbard shows existence by showing that your solutions in backward time are coming into these null-clines, and showing that the only way this can happen is if you have this connection between the fixed points.
So in my imagination, when you want to prove stability of an object, the existence of which you don't know only by these analytical means, then how do you put your hands on that object in the computation? So
you reprove this, right, Blake? You prove the existence of the profile. So even if you didn't have this existence result, you kind of reprove it with the computer, right?
Yeah, so, okay, that's a good point. So at positive infinity, at that fixed point at the top left, we solve in backward time. So we solve using a contraction mapping principle, so that's rigorous. And then now we have this rigorous solver to get from that finite value away from infinity, negative infinity, all the way to almost positive infinity. So all we'd have to do to reprove it is say, okay, look, we're within a trapping region of the source. Yeah, so essentially we don't do that last tiny piece because it's already proven.
And in this reproving process, you also get tight enclosures for the profile. Is that right?
That is correct.
That's what you use in the stability process, in the stability proving process.
That's right. And so those, right, so that enclosure of the profile is then used in the coefficients of the A matrix when solving the Evans function ODE, right?
And in that sense, it's more than just reproving existence. You need more than reprove that. You need more than just existence. You need to have your object in your hand by these enclosures.
That's correct.
So that means that, strictly speaking, the old existence proof is not so helpful for your computer-assisted stability proof because you don't have the enclosure without reproving it. Right? So maybe what I said sounded complicated. I just wanted to say that you did more than just reprove.
You know, actually, now that I think about it, you make a good point, because I guess when we solve the Evans function on the right, we'll also have to have an enclosure of it on the right. So I guess we will end up proving it all the way across, right? Yeah, you're right. Yeah, good point.
Oh, yeah, I have another question, Blake. So do you expect this solution to be stable for all parameter values?
We do expect it to be stable because the double arithmetic computations of Humphrey, Ling, and Zumbrun show it stable.
For any parameter values, because there seem to be quite a few parameters in the problem.
Well, okay, so that brings up a really good point. So in that study of Humphreys, Ling, and Zumbrun, they do cover a very wide swath of parameter space, but they don't do it rigorously. It's just with double arithmetic. I mean, it's numerically well conditioned and all that, right? So it's a very good study that gives very strong evidence for stability everywhere. Okay. But without some sort of analysis to say you've captured a dense enough sampling of the space, okay, we can't say, right?
But dynamically, nothing exciting going on where it becomes unstable somewhere?
No, it appears stable everywhere.
Okay, thanks. Any other questions?
Yes, I have one.
Mm-hmm.
Actually, regarding the contour, did you have a slide? Maybe I missed that, but regarding the contour that you need to do, which function exactly do you need to evaluate along the contour? I mean, how?
The Evans function, so d of lambda,
Right.
that
So
we've defined.
yeah. So how do you, so in practice again, how do you do that computation of the contour integral? How do you do it? You do it.
Oh, okay, right. So first, what we'll do is get a really rough bound with pen and paper on the Evans function.
Mm-hmm.
And then we'll use that bound to provide us with an error estimate on the interpolation error for a given number of nodes using this analytic interpolation error result. And so then once we determine the number of nodes, those are Chebyshev nodes, we pick those along the contour. So we're actually parameterizing the contour with an interval -1 to 1 so that the Chebyshev polynomials match up.
Mm-hmm.
Okay, so but it's an analytic function still that we're interested in. So then we interpolate. So we use our rigorous enclosure of the Evans function at those points, those Chebyshev points, to get our interpolation. And then with that polynomial, now it's easier to use interval arithmetic and then just compute all along it with intervals so that you can show the winding number is 0.
Mm-hmm. Okay.
So you compute the winding number by doing this integral with this argument principle.
That's right.
Yes. So it's not the integral of the Evans function itself, but of the derivative divided by the Evans function, right?
Well, so actually,
or not?
Actually, all you've got to do is look at the winding of the image, so you don't have to deal with the derivative at all.
Okay.
It's just the Evans function.
Okay.
Okay. Thank you.
Thanks.
I have another question connected with this contour again. So you said you take half circles, but then, so to say, the straight part of the half circle then crosses lambda equals 0, right? And there is an eigenvalue.
That's okay.
How do you avoid that? You get that? How do you avoid the singularity of this contour?
Okay, thank you again. Something I forgot to mention. It's probably why we ended so early. So the coordinates we're using in the end are integrated coordinates. So there's the standard trick you can do where you look at the integral of your variable, and when you look at it in those coordinates, it removes the eigenvalue at 0 corresponding to translational invariance. So in the end, the spectrum, I should mention, well, okay, never mind. Yeah, so then that eigenvalue is removed and you can go straight down the imaginary axes.
Okay, so you transform this eigenvalue out by
That's right, by using what's called integrated coordinates.
Is that connected with a phase condition or so if you use?
So what are integrated coordinates?
This integrated coordinates, I don't know that expression.
Okay, let me hold on just a second. Let me pull up. I can show you that transformation. Just give me a second. Or okay. Let me share my screen again. So this is for isentropic gas, but it's the same thing. So if U and V are your variables for the eigenvalue problem. Then you integrate them from -infinity to x. And when you substitute that in, you get this, this PDE in those new coordinates. And it takes out the eigenvalue at 0. But all your other eigenvalues remain the same with the same multiplicity.
Yeah, okay.
And I guess, you know, I guess you could, I'm kind of seeing your comment about a connection with the profile, because the eigenvector corresponding to lambda equals 0 is the derivative of your profile, and this is sort of like integrating it out. Yeah.
Okay.
Yeah.
I understand. Yes, I see. Thank you. Yeah. That's a nice trick.
Yeah, it's not ours.
Well, okay. Anyway.
But I just wanted to make sure I was. It is a beautiful trick, and we use it all the time. And I just want to make sure that it's clear it wasn't ours.
Okay. Thank you.
Nice. Any remaining questions?
Well, if I may, I have one more, which is a little bit like an outlook. So when we want to look at the real Navier-Stokes problem, which is a three-dimensional thing, then you are away from this spatially one-dimensional consideration. Then, of course, many things you did cannot be done. So, for example, the Evans function doesn't work. You cannot work with fundamental systems and all that. So it's clear that this is not so obvious how to generalize. So do you have a view on that? And one particular question, one particular question I have, when one wants to attack this higher dimension problem. So you said you cited a paper which said that spectral stability implies nonlinear orbital stability.
Right.
Is that limited to the spatially one dimension, or is that true also in higher dimensions?
No. So they've so Zumbrun and collaborators have shown it for higher dimensional.
Okay. So that's not
well.
That's not an obstacle for higher.
No, but you point out that showing spectral stability for the multidimensional case is a big open problem. There's been a lot of excitement and work around that. For example, there are those who work with Lagrangian planes, and they are using sort of a geometric interpolation. So think of, there's a paper by Deng and Jones, I believe, and that sort of started this off, and now there's been quite a bit of progress in that direction. But it's not a done deal yet. There's I know of like Bjorn Sandstede and some collaborators that worked on, I believe it was Swift-Hohenberg, where they use kind of a discretization. Anyway, so they're different. I know Levesque and collaborators have done some things. And I know there are lots of others, but I mean, these are some of the people. Obviously, my PhD advisor and my postdoc mentor, I'm going to be more aware of their stuff. But yeah, so there's a lot of interest. There's a lot of interest there, but yeah, it's still a big open problem how to do it.
Is there anyone among these people you're mentioning who do that by computer assistance, or is that all analytical work?
So their work's all analytical. They definitely have, I know some of them have in mind to try and create a condition that could be checked as a computer-assisted proof.
Okay.
Yeah. And then I know there are people, I mean, you work with multi-dimensional PDs. I know there are people in this group that are working on that. Jan Bauer, we heard his talk. I mean, there are a lot of people in this group that have been working on it. Yeah, so I don't know. I think the future might be bright, but there's a bit of work still, right?
Okay, yeah, thank you.
That seems a good final message for this talk, I would say, Blake. So I propose we leave it at that for today. Thank you again, Blake.
Thank you.